So hello everyone. This is ninth lecture in solid state physics, and we were discussing superconductors last time. If you have not seen the last lectures or the previous lectures, please go visit them first. Then it will be easy for you to understand these. Okay, we are just moving in the sequence. So in the last time we discussed about the thermal properties of the superconductors and how the entropy and thermal conductivity vary with temperature. So moving in that forward, today we're going to discuss the specific heat. So we know that superconductors are metal, and also they are alloys. Ceramics also are superconductors. So there are some examples like lead, niobium, mercury. We know them. Below less than Tc, when temperature is less than Tc, these are what? These are superconductors. And above Tc, they are normal conductors. The specific heat. So if we talk about the specific heat particularly, then for any normal atom metal, there is specific heat formula, that is Ce plus Cph. Here C is electronic specific heat and Cph is phonon specific heat. The net specific heat is the sum of both of them. And what is phonon specific heat? So you guys know that what is phonon. Phonon is a vibration in a solid that can be monoatomic or diatomic. So we're gonna study in detail about this Cph in the next sections. Here just remember this, what is this is because of phonons. This is because of electronic specific heat. Okay, so at low temperature means temperature is still greater than Tc, but it is nearby Tc and greater than Tc. Then we define C by AT plus BT cube. Here AT for Ce and BT cube for Cph. Okay, but when temperature goes down than Tc, when T is less than Tc, then some electrons convert into the Cooper pairs. We know what are Cooper pairs. Cooper pairs are the bound electron, two bound electrons, and these are bosons. Fermions are those have integral in the fraction spin, and in bosons we have the integral spins. So Cooper pairs are bosons because minus half plus half gives zero. And electrons are fermions. Okay. So below Tc, the formula for specific heat will be Ces plus Bt cube, and Ces is specific heat due to super electrons. Okay, and that is electronic specific heat. So because the Cooper pairs are gonna form, so only the Ces factor gonna affect, not this, because phonons are remain as it is, they won't affect it, but Ces will be affected because that is depending on the electrons. That's why the formation of super electrons will affect the specific heat below Tc. Okay, so there is no theory developed to find the analytical expression for the Ces still. So we just observed its graph, and graph can be visualized here. So when we take the observations, then graph came, just neglect this portion. This is, I cut it this portion. When we decrease the temperature from high temperature to reaching Tc, then it is a linear curve. Okay, because it is like this, only vary with this formula, and this is linear. So Ce, this is for Ce exactly. So Ce is greater than Tc. For greater than Tc, it is 80. So 80 is a straight line with slope a. So it is gonna, this is straight line up to Tc. But when temperature is less than Tc, then there is this discontinuity at Tc, and the graph gonna come this like this, when it was supposed to go like this, but it is going like this. So there is discontinuity at Tc for the superconductors at Tc, and when we are talking about the Ces. Okay, so this would be going like this is going like this, and this curve is can be mathematically solved by the exponential function. So this is actually exponential. So here Ce is directly proportional to e to the power minus Eg by 2 kt. So we know that when there is Well, we will talk about it later. First, let's discuss some things coming out of this graph. So at T equal to Tc, there is discontinuity in specific heat. No latent heat involved in normal transition. When there is a transition from normal to superconductor, normal to superconductor phase transition, there is no latent heat involved. So you guys know what is latent heat. So latent heat is the amount of heat required to change the state of a substance or anything. Okay, so there are some terms like first order transition, second order transition. So you guys must heard about it. Volume remains constant during phase transition, and this is normal to superconductor transition is second order transition, second order phase transition. Just like ferromagnetic to paramagnetic in the magnetism, when we decrease the temperature, then it convert into this. Okay, so if we talk about the some first order transition also, here it is example of second order. For the first order transition like water to vapor conversion and the water to ice, ice to water, these are called the first order phase transitions. So there are some numbers you should remember, like if you want to convert water to vapor, then amount of heat required is 40 kilojoule per mole. Okay, heat absorbed, that will be absorbed to convert the vapor now. And for water to ice and ice to water, there is this 80 calorie per gram heat released for the water to ice, and heat will be absorbed for ice to water. So these are the number 40, 80. So you can remember this like 80 for 18 calorie and 14 kilojoule. So we were talking about this, that it is exponential function. Okay, so when we see that any graph is in exponential way, then the outcome is, or what we observe from this, that the graph is not continuous, it is discrete. It is discrete at levels. Like when it is depending on temperature only in the exponential function, then this will be discrete. So how it will be? Like we studied that if there is two states n0 and n1, and there is delta E difference in energy gap, then n1 by n0 can be defined as e to the power minus daily by kt. So there is this difference, discreteness in the levels. So that's why from this graph we take this outcome as this will give us the discreteness, and discreteness will give us the energy band gap in the superconductor. So from this expression, we see that CES is, there is some constant, we take the proportionality constant d e to the power minus eg by 2 kt, and this whole function indicates, as we already told you, that discreteness is there. So this indicates some energy gap in superconductor. And how to find this energy gap now? It's very easy, just take the log of both sides. Log of CES will give us log d minus eg by 2k 1 by t eg by 2 kt. Okay, that will be just log. Now we can plot natural log of CES with 1 by t. Then it will be equation like y equal to mx plus c. Here m is slope, which is minus eg by 2k, x is 1 by t, and c, the y-intercept, is log d. So this is the equation of line. It will cut here at log d, and slope will be minus eg by 2k. Here k is the Boltzmann constant, and eg band gap in superconductor. So we can find from now from this graph the band gap is just a 2k multiplied slope. Okay, we're gonna discuss about the band gap. Let's discuss the energy band gap now. It's the better time. So what is energy band gap in the superconductor? In normal case, we know that when we reach at the absolute zero temperature, T equal to 0, then this Fermi energy level, all the electrons will be found in the lower state than this. This is the maximum energy state at T equal to 0. Okay, but when temperature is greater in the normal cases, the electrons can be found on the upper side. Okay, upper sides. So what happens when temperature decrease? When material is cooled down below T less than Tc, some electrons above EF make bound state. Bound state means that is Cooper pairs. These Cooper pairs are formed by releasing easy amount of energy. Now when these electrons upper, when temperature is decreasing, then they form the Cooper pairs and they will come down, and there will be the release of this energy Eg. That will be the energy band gap, are formed by releasing easy amount of energy, and they settle down below EF. Okay, so the energy can be given by this expression. You should remember this. You can use this direct formula to calculate the energy in the questions. 2 into 1.75, that will give us 3.5 kb Tc. Here kb is Boltzmann constant. So E is equal to 10 to the power. This gives us for the normal 6 Kelvin critical temperature 10 to the power minus 4 electron volt. This is very less actually. It's in milli electron volts. This energy we found in the superconductors. Okay, so from these expressions or these observations, we see that energy band gap is also is a temperature dependent. Yeah. So there is this formula: Eg at any temperature T divided by Eg at 0 will be equal to 1 minus T by Tc to the power 4. So when T equal to 0, we find that Egt equal to Eg0, Eg0 we can say that. So and at T equal to Tc, Egt will be 0. Okay, so here is this graph. This is if T equal to 0, then we find that Egt equal to Eg0, and when Ez equal to 0, sorry, when T equal to Tc, then that will be Eg will be 0. So we get this graph. This is normal, this is superconductor, and this is energy at any temperature T. So here we end with the thermal properties. In the next lecture, there are 1 or 2 lectures more just for the superconductors. We're going to study about the Josephson function and the BCS theory, and we will end this. And next, we will start a new topic that will be the lattice vibrations. So today we end here. Just revise all the previous lectures and this. Okay, thank you.